Patterson, and today we're going to go over biochemistry. So what does chemistry have to do with biology? And a lot of it is that life is dependent upon chemistry. We have certain chemical reactions that you need to have in order to stay alive. If these chemical reactions stop, your life, the life of an organism, will also stop working. So you think of breathing. When you breathe, you respire. You're bringing in oxygen. You're getting rid of carbon dioxide. A chemical reaction happens inside your body to do that. Plants use chemical reactions, photosynthesis. Sunlight comes in. They turn that into sugars, and your body or the plant will produce oxygen as a waste. It's going to bring in carbon dioxide. And when you eat, you're doing chemical reactions. So when you had lunch today or breakfast this morning, your body is doing a chemical reaction to break down those foods. So all living things are made of matter, and matter is composed of atoms. So atoms are the smallest particle that contains a mass. So you have protons, which are the positives. You have neutrons, which are the neutral, which are the ones that will have a neutral charge. And then you have electrons, which are on the outside in the orbits or the shells. These are a negative charge. Inside the center, the protons and the neutrons together make what's called a nucleus. And the nucleus also has a positive charge because I have positive protons and I have neutral neutrons. So this whole nucleus has a positive charge. So when we talk about atomic mass, it's the total mass of protons and neutrons in that nucleus, so that center of that nucleus. So protons will have a positive charge, and I have a mass, it's about 1 AMU, and it's found inside the nucleus. You have neutrons, which have a neutral charge. The mass is very similar to a proton, and that is also found in the nucleus. I have an electron, its mass is so small that it doesn't really accumulate a mass on the atom, so we don't count that in for the atomic mass of the atom. So the electron itself is 1/1840th of the size of a proton or a neutron, super small. So here I have a nucleus, and then here I have my first orbit, and that first orbit will hold 2 rings. So this is kind of like our Bohr model that we talk about. I have a second ring. The maximum I can have on that one is 8 electrons. And then I have a third ring. The maximum I can have on that one is 18. Once the ring fills up, so if I have 2 in this one, I can never put 3 on this first ring. I'll have to jump to the second ring till I fill that one up with 8. After I have 8, I have to jump into this next ring. So I can't add more than 8 electrons in the second ring. I cannot add more than 2 in the first. I cannot add more than 18 in the third ring. And there's more that we go into later, but for what you need to know right now, that's good. So the atomic number. This is the atomic number up here, the one that goes in numerical order. So 1, 2, 3, 4, 5, 6. That's your atomic number. That tells you the number of protons in that atom. And the protons is what makes that atom that atom. Carbon has 6 protons. That's what makes it carbon. If I add a proton to carbon, I get nitrogen. If I take a proton out of carbon, I have boron. And those are completely different atoms, different elements. So here I have carbon. And then here I have the makeup of carbon. I've got my 6 protons, 1, 2, 3, 4, 5, 6. When I look at my atomic mass, it's the addition of both protons and neutrons in the center. So if I have 6 protons, I have to have 6 neutrons, and I do. That takes the mass. This atomic number also tells me the number of electrons I have. So if I have 6 protons in a neutral atom, I'm going to have 6 electrons. So here I have this element. This plus means protons. So a +3 is going to be lithium. That's protons for lithium. And so I'm also going to have 3 electrons. Then I have the next one, which is 9. If you have a periodic table, I'll give you a second. You can look and see which one that is. That one's fluorine. I look here, I have 13. I have 2 in the first ring. I have 8 in the second ring, and then I have 3 in that third ring. So this is my orbital configuration for aluminum. So what is an element? An element is going to be anything I can find on the periodic table. It is something that I cannot break it down into a smaller atom, a smaller element. So let's look at gold. Gold is right here. It's on my periodic table, so it's an element. I look at water. Water is H2O. I cannot find water on here, so it's not an element. It's a compound. I have hydrogen and I have oxygen. So if I can break it down into smaller parts, it's a molecule, it's going to be a compound. This one's a compound because I have 2 different elements. So 99% of the mass of living things are made up of 6 elements. So all living things are going to have these. It's going to be carbon. So when they talk about humans are a carbon-based life form, we have a lot of carbon in our system. We also have a lot of calcium. We have hydrogen, we have oxygen, we have nitrogen, and we have phosphorus. So what's an isotope? So an isotope is going to be an element that has different number of neutrons from the standard element on the periodic table. So here I have hydrogen. Hydrogen has 1 proton. Hydrogen does not have any neutrons in its natural state in the periodic table. If I add a neutron to it, I now have changed it into an isotope. I have added a neutron to it. Here I have hydrogen 3. This has a larger mass. I have more neutrons than normal, so therefore that is considered an isotope. So here I have a common isotope we talk about a lot in biology, carbon 12. This is the standard carbon that we find on the periodic table. I have 6 protons, I have 6 neutrons, so it gives me a mass of 12. If I put another neutron in it, I now have an isotope. I've added 1 extra neutron, so now my mass is 13, so I have carbon 13. Carbon 14, I have 2 neutrons that have been added to it, so now my mass is carbon 14. Radioactive isotopes, they can be pretty unstable. So they break down at a constant rate over time. They are used to date rocks, fossils. They're able to treat cancer and kill bacteria. They're able to be tracers. You can ingest or they can inject certain types of radioactive material and it will go through your body and it will go through your organs, and then when you see it through an x-ray, you can make it out. So here I have these organs that have the radioactive tracers in them. What is a compound? It's a chemical combination of 2 or more different elements in a fixed ratio. So I look at gold. Gold is just Au. I only find it on the periodic table. I have water, H2O. I have 2 hydrogens and 1 oxygen. I can break this down into smaller pieces, hydrogen and oxygen. I cannot do that with gold. Au is gold. I cannot break it down anymore. I have O2 gas. O2 gas is not a compound because all I have are oxygens together. Even though I have 2 oxygens, it's not a compound because I have 2 of the same type. So physical and chemical properties of compounds. Properties of a compound are usually different than their individual elements. So a good example is salt. When I have salt, I have sodium, which is Na. This is a very soft metal. I can cut it with a butter knife. It cuts real easy. It's really reactive with oxygen. I have chlorine, which is a green gas. It's toxic. It can kill you. But when they're bonded together, I get these salt crystals that we can use on food. Your body needs it. So this is a elemental compound that we need inside our bodies. But when I break them down, they're toxic. I have chemical bonds. These are bonds that are formed by the electrons in the outermost shell, or sometimes we call it an orbit. So this is a shell or an orbit. So these are where your electrons are going to live. The valence electrons are the ones that live in that outermost shell, the outermost ring. When we talk about chemistry and we talk about bonds, like 90% of chemistry are the valence electrons. Where are they? Who's got them? Where are they going? And if you can figure out that, you can figure out the bonds of what's going on. So you have ionic bonds. These are going to transfer steel valence electrons. They're going to be between a metal and a nonmetal. So when you look on your periodic table, you'll see metals on one side and you'll see nonmetals on the other side. These are going to create ions, which means I have more electrons or less electrons than normal, and they're stronger than a covalent bond. So let's look at salt. NaCl is a common formula for salt. So why are these two elements attracted to each other? So the first thing we need to look at are their valence electrons. So we look here at chlorine, and chlorine has 7 valence electrons, and I know that because it's in group 7. Group 7 means it has 7 valence electrons, so the up and down columns are your group. When you look up at chlorine, look at the top of the group, it will say 7 or 17, and that means it has 7 valence electrons. Sodium is in the first column, so sodium has 1 valence electron. So this wants to go here. This one wants to fill what's called the octet rule. It wants 8. It either wants 8 or it wants none. So this electron is going to be given to chlorine. It's going to want it. Sodium's going to want to give it away. So it's going to move over. So it's easier for chlorine to gain 1 electron than it is for it to lose 7. So sodium is going to be easier to lose 1 electron than it is to gain 7. So it's going to take less energy for them to do that. So chlorine needs 1 more electron to be stable. Sodium needs to lose 1 to be more stable. So chlorine's going to be like, hey, can I have 1 of your electrons? And sodium's like, sure. The electron's going to go. Now chlorine is going to be a full shell. It's going to have an octet rule. It's going to be like a noble gas. And sodium is now going to be like a noble gas because that outer ring that had 1, that inner shell right below it is now full. So it's also going to be very similar to a noble gas. It's more stable. So now sodium is going to want to be closer to chlorine. Chlorine has more negative charge because it has more electrons. Sodium has more positive charge because it has less electrons. It has more protons. So now chlorine and sodium are bonded. They're going to make the compound salt. And now we got to write this out. So we have to show our charges, our ionic charges. So did chlorine gain or lose electrons? It gained 1 electron. So chlorine's more negative by 1 electron. And a way to see this is to write it out. So chlorine here has usually, or it always has, 17 protons, and it usually has 17 electrons if it's neutral. But chlorine just gained 1. So chlorine no longer has 17 electrons and now has 18. So is it more positive or is it more negative? It's more negative. By how much? By 1. So I would write -1 next to chlorine, and that shows that it is a charge of -1. So did sodium lose or gain electrons? Sodium lost electrons, so sodium is now more positive. And again, you can see it here, sodium always has 11 protons, and when it's neutral, it has 11 electrons. But it lost an electron, so it no longer has 11, it has 10. So is it more positive or more negative? It's more positive by 1. So sodium is going to have a +1 charge. So now I can see that this positive sodium is attracted to this negative chlorine and vice versa. So this is going to be the attraction that's going to keep them together. So now the compound is neutral. It's also stable. So that's why you can eat salt on French fries and it doesn't turn into sodium and chlorine gas. So I have a 0 net charge. The compound as a whole is neutral because the sum of my charges on the ions is 0. We have covalent bonds. These are going to share between 2 to 6 electrons. They're going to be between 2 nonmetals. They can be 2 of the same type or 2 different types of elements. So here I have fluorine. Fluorine has 7 valence electrons and so it needs 8. So it wants one more. So this fluorine wants one, this fluorine wants one. So this fluorine can let this fluorine borrow one. So then for a little bit of time, this fluorine will have 8. And then every once in a while, this fluorine will have 8. So you're going to have a moving back and forth of electrons. They're going to pass back and forth so they can have that charge and they can have that full octet rule. I can do the same thing for water. Oxygen is in group 6, so I have 6 valence electrons, so it needs 2 more to be stable to fit that octet rule. Hydrogen has 1, and hydrogen wants to be like helium, so it wants 1 more in its first ring. So they're going to come together. So oxygen is going to keep a lot of the electrons around here. Every once in a while, it will give hydrogen an electron, so it can have 2 go here. But it's going to kind of go, and it's going to allow a little bit, but it's a different charge. Oxygen is super electron negative, and so it's very greedy for electrons. It's going to want to keep the electrons around the oxygen a lot more than it's going to let the hydrogen. And we'll talk more about that here in a minute. So we have polar and nonpolar bonds. Polar are going to share unevenly. Nonpolar share evenly. So here I have this little symbol is your electronegative symbol. And if I have an element that is very electronegative, it's very greedy for those electrons. It wants to keep all those electrons and not let them go. It's kind of like a kid with their favorite toy. They're not going to let other people play with that toy. And if they do, it's just for a few seconds and they're going to pull it right back. And that's kind of how you need to think of oxygen. Oxygen's that way. It's going to keep all the electrons, and every once in a while it's going to be nice and just let hydrogen have 2 electrons for a second, and then it's going to pull it back. But it's going to stay here most of the time. So when it stays here, I'm going to have a negative charge. I don't know why that says positive. That should be negative. But this will have a negative charge, and then the hydrogens up here will be a positive charge. So this is going to have a positive charge most of the time because my electrons are gone. My electrons are hanging around my oxygen. My nonpolar covalents, I'm going to have a similar charge, so they're going to be just shared evenly, so they're just going to keep going back and forth. I'm not staying in one spot very long. And then here I have another nonpolar oxygen. They have similar electron negativity, so one won't keep longer than the other, so they're just going to go back and forth real quick. It's when I have a change in charge, like between oxygen and hydrogen, that I'll see those polar pools. So covalent bonds are here between hydrogen and oxygen, but oxygen is still so greedy for electrons. It wants them so bad that even the ones that it has, it's not happy with. It still wants more. So it's trying to pull these electrons off these other hydrogens, but it can't, because remember its orbit is full. So it can't take any more. But the charge, this electric pull, is enough to keep these hydrogens close together. So when we talk about these bonds, these solid lines, these are covalents. Electrons are actually being passed back and forth. Here between these hydrogen bonds, there are no electrons being passed back and forth, but you need to think of it like a magnet. It's kind of pulling towards those oxygen atoms. So this is another reason why you can take water, and I can run my finger through water on a table and the water will break apart and it will come back together. Or if I have water running down my windshield, if it's raining and it beads up and clumps together, these little bonds break and come together so much because there is no real big change of material back and forth. It's just this magnetic pull. So hydrogen bonds break apart, come back together super easy. All right, so that's it for right now. That's going to be all that we've got for this part. And if you guys have any questions, let me know. Talk to you later.